Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to loading effects. Okay. So far we have discussed loading effects with respect to input impedance and input admittance. In this video we are going to discuss about loading effects with respect to output impedance and output admittance. Now we all know the basic concepts related to loading effect. So loading effect basically is the inability of a system to faithfully produce the exact original signal which it receives at the input side. Okay, so simply saying that when a signal, input signal let's say, is passed through a particular block or a system, the output which we get is not the same, exactly the same as the input, which is because of various reasons such as distortion, power loss, attenuation, like that, various reasons. So when the number of systems increases, all these things also increase, and as a result the output which we get is not the same as the input. So that exactly the mismatch between the input and the output is because of loading effect. So previously we discussed loading effect with respect to input and impedance and input admittance with respect to voltage and current sources. So here we'll try to understand it with respect to output impedance and output admittance. So here we have the output impedance here. We have a device, then we have a load impedance connected to it across which we have to get the final output. Okay, the final output. So this device, it can be anything. Okay, it can be a sensor circuitry, signal conditioning circuitry, any measurement device, whatever you want to visualize you can. But we need to simplify this the circuitry of this device. So we are using Thevenin equivalent circuit of this device, that is a voltage source in series with a Thevenin impedance. So that we are calling it as the output voltage E0 and the output impedance Z0. Okay, so as we are dealing with the output side, this is the output impedance, the factor which we are interested in. This is the output voltage. There is a difference between output voltage and load voltage. EL is load voltage. Okay, now when we apply KVL in this loop, we get E0 minus IL ZO minus EL is equal to 0, or we can write it as IL ZO is equal to E0 minus EL, or we can write the output impedance ZO as E0 minus EL by IL. Now what we want is that the load voltage should be as close to the output voltage. The load voltage should be as close to the output voltage. But actually this is the case. E0 is equal to EL plus IL Z0. This is the voltage drop. Okay, this IL Z0, the voltage drop across the output impedance. So this causes some loss, because of which the load voltage is different from the output voltage. So we have to minimize this loss. So how we can minimize it? We have to minimize the drop. the voltage drop. How we can minimize the voltage drop? So here if Z0 is low, then IL Z0 drop will also be low, and less the IL Z0 drop, the closer the load voltage to the output voltage. So for faithful reproduction at the output side, the output impedance should be low. The output impedance should be low. Okay. Ideally, the output impedance should be 0. Ideally, output impedance should be 0, but it is not possible. There will be some output impedance because of which there will be distortions, but we have to minimize it by ensuring that the output impedance is low. Another way to look at it is the power loss in this device. The power loss in this device. So here this is E0 minus EL into IL. Okay, E0 minus EL into IL. The power loss in the device is equal to E0 minus EL into IL. Now we know E0 minus EL is equal to IL Z0. E0 minus EL is equal to IL Z0. If you take IL to the left side, it will come into numerator. So we can write it as IL Z0 into IL, which is IL square Z0. We know less the power loss, distortion is also less. So in order to minimize the power loss, we have to minimize Z0. So lower Z0 means lower power loss, it means lower distortion, means more faithful reproduction of the signal. Okay, so for output impedance, it should be low, ideally 0. Okay, output impedance should be low. Then we have to deal with output admittance. Again the same thing, but here we are using Norton equivalent circuit. Now I have always told that when we deal with impedance, it is convenient to express the circuit in terms of voltage source. Here we are dealing with impedance, output impedance, so we represented it in Thevenin equivalent. Voltage source in series with impedance. Here we are dealing with admittance, so we have represented it in terms of Norton equivalent circuit. Current source, the output current, and the output admittance. It is the same. Admittance is simply, here the output admittance is simply the reciprocal of the output impedance. Okay. So here if you write Z0 also, it is not problem, there is no problem. Z0 will be simply reciprocal of output admittance. So no problem whether you write here Z0, Y0, there will be no problem, but you have to bear in mind that whenever you use it for calculation purpose, it is the reciprocal of each other. Okay. So now here, let us say we have written here admittance, so let us say it is Z0 here, okay, admittance, impedance. So here the output current is I0, it is flowing from here, I0. Here load current IL is flowing, so as a result the current flowing through this output impedance or output admittance, it is I0 minus IL. Okay, I0 minus IL. EL is the voltage across the load. Okay, same voltage here also, it is EL. So we can write Z0 is equal to EL by I0 minus IL, or we can write output admittance as I0 minus IL by EL. That implies I0 minus IL is equal to Y0 EL. Now what we want is that the load current should be as close to the output current. In the previous case, what we wanted, the output voltage should be as close to the load voltage. Here it is the same thing. As we are dealing with current source, Norton equivalent circuit, we want the load current should be as close to the output current. But here it is I0 is equal to IL plus Y0 EL. Okay, this. So in order to, because of this factor, there is fluctuation between the output current and the load current. So what we can do is that if we can do something with this factor Y0 EL, then we can minimize the difference between I0 and IL, output current and load current, close in the gap. So for that what we need is that Y0 should be less, it should be low. The output admittance should be low, or we can write it in a different way as the output impedance should be high, because they are reciprocal of each other. So never get confused. Admittance is the reciprocal of impedance, whether it is at the input or output. Whether you write Y0 or Z0 does not make any difference, but you have to keep it in mind that they are the reciprocal of each other. Suppose you say high output impedance, it is the same as low output admittance. It's the same thing. Okay, so you can say high impedance or low admittance. It is the same thing. So output admittance should be low, or output admittance, output impedance should be high. So then this extra factor will be less, and I0 will be as close to IL, which we want. Okay, so another way to look at this is that the power loss in this device, okay, the power loss in this device is simply I0 minus IL into EL. Okay, I0 minus IL into EL, product of voltage and current when it comes to this device. This device is represented with the help of the Norton equivalent circuit. So here the voltage across this device is EL, current flow is I0 minus IL, so it is this. So now I0 minus IL, we can substitute it as I0 minus IL as Y0 EL. We can write it in that way, or we can write it as in this relation, Y0 is equal to I0 minus IL by EL. So then this will be simply EL square Y0. Okay, EL square Y0. Simply from this, I0 minus IL is equal to EL Y0. So it will be EL Y0 into EL. So don't get confused here. I simply substituted I0 minus IL with EL Y0. So here this is the power loss. So here we want less power loss, that will be less distortion, and the only way to achieve that is when Y0 will be less, the output admittance should be less. So that means more faithful reproduction of the signal. So any way you want to deal with it, the output admittance should be low or the output impedance should be high. So high ideally means low. When we say low, ideally it should be 0. When we say high, ideally it should be infinity. Okay, when we say low, ideally it should be 0, and when we say high, ideally it should be infinity. But this ideal thing is never possible, so we stick to low and high. Okay, So when it comes to output impedance and admittance, okay, output impedance, that should be low. Output impedance, it should be low when it comes to voltage sources. When it comes to current sources, the output impedance should be low or the output impedance should be high. Admittance should be low, impedance should be high. So that is, it is very easy to get confused. So always stick to the basics here. For voltage sources, impedance should be low output side. For current sources, impedance should be high for output side. And then for the input side, when we are dealing with input side for voltage sources, the input impedance should be high. The input impedance should be high, ideally infinity, and the input admittance, okay, the input admittance when it comes to current sources, that should be high for current sources at the input side. So here we have discussed loading effects with respect to measurement system. So let us summarize the whole thing with respect to loading effects, which because we have discussed a lot. So basically in loading effects we dealt with voltage and current sources, both at input side and output side. So we categorize it into two categories: voltage sources, current sources. For voltage sources at the input side, the input impedance should be high. Input impedance should be high, ideally infinity. Or we can say the input admittance should be low, ideally 0. Okay? Then for current, same input side, dealing with current sources, the input impedance should be low, ideally 0, or we can say the input admittance should be high, ideally infinity. Okay? Voltage and current input side is done. Then output. For voltage sources output, output impedance should be low, ideally 0, or we can say the output admittance should be high, ideally infinity. Then this is for voltage sources output. Then current sources output side, we can write it as current sources output side. The output impedance should be high, ideally infinity, or the output admittance, it should be low, ideally 0. So I have given both ways of representing this. Suppose you write input impedance is high, it automatically means that the input admittance is low. So you can use any one of the following. If you say input admittance is low, it automatically means input impedance is high. Similarly, if you say the output admittance is low, it automatically means that the output impedance is high. So you can use any one of the following. So if you are comfortable with impedance, remember the impedance parameters for all of this. If you are comfortable with admittance, remember, or no need to remember, just by looking at this circuit, when you visualize this circuit, any one of the following circuit, you will automatically get, okay, Ohm's law, this is the current and voltage relationship, this is the power extracted, low power extraction, low distortion, then we will automatically get these things. So normally people are comfortable with impedance parameters. So you remember the impedance parameters for both voltage and current at the input and output side. Okay. So here we have discussed about loading effects with respect to input impedance admittance, output impedance admittance. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.